Students, this is a classic problem dealing with reaction kinetics. They're giving us time data and concentration data for a reaction. And they tell us that we're talking about a decomposition reaction of hydrogen peroxide. Decomposition is the type of reaction where you start with typically one reactant and you form two or more products. So our lone reactant is the hydrogen peroxide. To figure out what type of reaction we have, we need to enter we need to do some entering of data in our calculator. So if you go to your stat menu and hit edit, so stat and then edit, presuming you have a TI calculator, in your L1 column type in all of the times. In your L2 column type in all of the concentrations. This much is manual entry, so you have to actually type in the list. It won't take too long, but go ahead and enter L1 all the times, L2 all of the concentrations. In the other columns, you can do a shortcut. So for L3, if you highlight L3, and then hit enter, and then type in natural log, and open parentheses will open up, and then hit second and the number 2, and what'll show up is L2. What you're telling your calculator to do is to populate list number 3 with the natural log of all the numbers that are in list 2. So effectively, what you're making is the natural log of H2O2. L4, we're going to do something similar. We're going to say 1 divided by L2, which will give us 1 over the concentration of H2O2. Once you've got your lists populated, then we're going to hit stat plot. So on TI calculators, that's typically in the very upper left corner. So hit second and the Y equals button. And under XList, let it be L1. And keep it there. So regardless of which plot that we're looking at, we want time on the X-axis. For the Y list, this is the one that we're going to do some changing. Try L2 at first. And then hit zoom stat. So second, or zoom and then option 9 at least on a TI-83. Zoom stat to get a good viewing window on the data. And ask yourself, does that plot look like a straight line? And when we're looking for a straight line, I mean exactly straight. If not, then go ahead and plot L1 against L3 and zoom stat and see if that's a straight line. And it's got to be exactly straight. And if that's not the case, or even just to double check, even if it is the case that L1 versus L3 was a straight line, go ahead and plot L1 against L4. Only one of those plots, L1 versus L2, L1 versus L3, and L1 versus L4, will give you a straight line. And the one that gives you the straight line will tell you what type of reaction, or what reaction order we have. In this case, when you hit zoom stat, you should get a beautifully straight line when you plot L1 against L3. So that means the natural log of H2O2 plotted against time gives us a straight line, and then that tells us that, hey, we've got a first order reaction. That's going to tell us everything that follows. We've got to get that determination right at the beginning. So if we know it's first order, then answering the first couple of questions is pretty straightforward. The differential rate law would be the only one who's got a sum of exponents equal to 1. The integrated rate law just follows the format of any first order reaction, and you can find that in our table of integrated rate laws for each of the reaction orders. And then to find the rate constant K, there are a couple of different strategies. One is you could say, all right, I'm going to use my calculator, and I'll hit stat and then calc and then linear regression. You'll get this function that says linreg, and then in parentheses it'll say ax plus b. You may need to hit L1, L3 so your calculator knows which of your stat lists it's taking a linear regression of, or it might self-populate. If your only lists are L1 and L3, I think it'll do that automatically. But when you hit stat calc linreg L1, L3, you get a value of A being the slope, of negative 0.0083. And if we know that we have a first order reaction where natural log of the concentration of the lone reactant against time gives a straight line, the slope is always negative K. The slope of this kind of a plot is negative K. So if we've got a value of the slope that's a negative 0.0083, then that means the value of the rate constant is then a positive 0.0083. Or if you're into scientific notation, 8.3 times 10 to the negative fourth. Okay, that gets that one. And then the last question is one that we're going to have to use the differential rate law. If we know that we have a first order reaction, and at this point we know the value of K, we can say, all right, the natural log of the concentration of H2O2, which is what they want us to calculate, is equal to 0.0083, that's the value of K, times the time, and they're giving us the time. Your red number may differ from mine, but it's whatever that red number is, plus the natural log of, here's where it gets a little interesting. If we're looking at the initial concentration of H2O2, I'm following the format of this integrated rate law down here. What the number we need to plug in this spot is the initial concentration of H2O2. Well, that number is given to us in the data table. The data table has the first row as time equals 0, and it actually gives us the initial concentration of H2O2 right there in the data table. And so we can plug that number in. It's 1. And then it's a matter of just carrying out the calculations. So we've got the natural log of our variable. If I pull out my calculator at this point, I get negative, oh, there should be a negative sign here. So for the K, the value of K, it's a negative K. I had initially forgotten to write that down. 3.4694, and the natural log of 1 is 0. Okay, so if I want to get the concentration alone in this equation, I'm going to raise both sides of the equation, raise e to the both sides of the equation's power. That gets rid of the logarithm, and we're left with, if we plug into my calculator, e raised to the negative 3.4694 power, and round to a reasonable number of significant figures, it's 0.031, and it's a concentration, so that's molar.